Hello, welcome back to my channel. This is Learn with Maki, and in this tutorial we are going to continue with what we started from lesson 1. So we are continuing with lesson 2, and in lesson 2 we'll be looking at vectors. But before we go into what vectors are, we should know what a quantity is. So what is a quantity? You say a quantity is any physical thing that can be measured. So anything that you can measure or you can put in measurement, you can say that thing is a quantity because it can be quantified. The two basic types are, we have the scalar quantity, and then the next other one is the vector quantity. When we talk about scalar quantity, then we are referring to any quantity that has only magnitude. So in other words, we say that a scalar quantity, okay, has the magnitude, but it has no direction. It's only, we can only measure the quantity, that is the magnitude. When you say magnitude, we can talk about the volume, or let's say the yes, the volume. We can talk about the volume, or let's say the amount of that particular quantity that we want to measure. So scalar quantity, they can only have the amount that we want to measure, that is the quantity or the magnitude. So scalar quantities, they only have magnitude. Example is temperature, and we have time, and also we have speed. Note that speed is different from velocity because speed has no direction. Then the next one, we say vector quantity. What is a vector quantity? When we talk about a vector quantity, then we are referring to that physical quantity that has both magnitude and direction. Okay, different from the scalar quantity. For the vector quantity, we can actually measure what you can actually measure the magnitude, that is to say the volume or the amount of quantity of that particular quantity. And then we can also know the direction in which that particular quantity we are measuring is taking. That is what makes the vector quantity different from the scalar quantity. Other types of quantity include, so aside the aside the scalar quantity and then the vector quantity, we also have other quantity as fundamental quantity. And we say that fundamental quantity is the simplest form of quantity that can be measured. Okay, so for this one, examples of the vector quantity, we have acceleration. Acceleration has both magnitude and direction. We also have force. Force has both magnitude and then direction. So those are examples of some of the vector quantities. Then when we say fundamental quantity, it's the simplest form of quantity that can be measured. So there are 7 fundamental quantities, and then some of the fundamental quantities, some of them that we have include mass. We have mass, we have length, we have time as a fundamental quantity. Also, we have amount of substance, that's amount of substance. We have amount of substance. We also have luminous intensity. We also have current. So those are some of the example or the simplest form of quantity that we have. Then let's talk about derived quantity. When we say derived quantity, then they are a combination of 2 or more fundamental quantities. So derived quantities, in other words, are obtained from fundamental quantities. Without fundamental quantities, we cannot have derived quantities. They are derived quantities because they are obtained from fundamental quantities. So examples of derived quantities, we have acceleration. We have acceleration. We have acceleration. We have velocity as a derived quantity, and we also have force. So if you look at acceleration, you realize acceleration has is mass per second squared here, right? Mass per second, that is meter per second squared. That is acceleration. And then the meters here is a basic quantity of length. The second here is a basic quantity of time, or fundamental quantity of time. So you realize that acceleration is made up of two basic quantities. In other words, velocity too has the same thing, which is meters per second. Meters is a basic quantity of length, then second is a basic quantity of time. Then when we look at force, force has from a formula of kilogram meters per second squared. The kilogram here is a fundamental quantity of mass, m is a fundamental quantity of length, s is a fundamental quantity of time. So derived quantities, that's what they are made of. They are made up of basic quantities or fundamental quantities. Now, with the background knowledge in what quantities are, let's look at vectors. When we say a vector, what is a vector? We have already established that a vector quantity has both magnitude and direction. Examples include force, velocity, and displacement. The magnitude of a vector is always taken to be a non-negative number. So if you want to measure the magnitude of a vector, we assume it to be a non-negative number. If we include a negative value attached to a vector, then you might be describing opposite, or let's say direction in other sense. It talks about direction, or let's say yes, direction in other sense. So for magnitude of vectors, we always assume or take it to be a non-negative number. Because most of the time, if you want to measure mass, you are getting a positive number. If you want to measure time, you are getting a positive number. If you want to measure the amount of substance, you are getting a positive number. So we often take the vector to always be a non-negative number, which means that only positive numbers. Then the next one, a vector is represented as a directed line segment, that is an arrow showing both magnitude and direction. So that is how a vector is represented. Now let's look at this image here. We look at the image, we realize that we are saying a vector is represented by a directed line segment. So the directed line segment here, which is the arrow, it shows the magnitude of the vector, and then the angle described here also shows the direction of the vector. Bear in mind, vector quantities have both magnitude and direction. And with the magnitude, the length of the arrow here describes the magnitude of that particular vector. Even though this is not drawn to scale, suppose it was drawn to scale, then the arrow will have varying length. For example, let's say I have a vector of 2 units and another vector of 4 units. If I want to represent and assume that they all have a direction that is at an angle of theta, then what it means is that if I should represent these two units, then it's going to look somehow like this. Let's say for the first one, this is the for the first one, let's say this is the horizontal line, and then the vector will be described here. at an angle of theta. Assume it's at the origin. The same way, if I want to represent to the 4 units with the same at the same angle, it's going to look like this. With my angle theta here, assume this to be the origin. So what it's basically telling us is that if we should draw vector quantities to scale, let's say we might use 2 centimeters. Assume that the length from point O to this point is 2 centimeters. Then the next arrow for the next vector is going to have a unit of 4 centimeters. That is when we decide to scale the vectors. The length of the vector describes the magnitude, and then the arrow, which is the angle here, also describes the direction of the vector. So it is not always the case that it moves in this direction. You can have vectors moving in various, or let's say different directions. For example, I can have another vector here moving, having this angle described here, theta here. Yes. So you can always have the vectors directed in different angles. So from comparing this one here to this one here, you realize they both have the magnitude, but then their direction is different. Okay, so that is the simplest way you can represent a vector, with the magnitude being the arrow and then the direction being the angle that it takes. So we look at addition and subtraction of vectors. Vector quantities obey the parallelogram law of addition. What is the parallelogram law of addition? The law states that when two vectors are added, the resultant vector is the diagonal of the parallelogram formed by the vectors. When two vectors are added, the resultant vector is the diagonal of the parallelogram formed by the vectors. Addition and subtraction of parallel vectors are, however, simple and straightforward. So let me talk about the parallelogram law, then we'll talk about the other one. So this is an image describing or showing the parallelogram law of vector addition. So in simple terms, let me create a space so I can talk more about this. Okay, so the parallelogram law is saying that when two vectors are added, the resultant vector is the diagonal of the parallelogram formed by the vectors. So assuming I have a vector here, assume I have a vector here. Let's call this E. The vector is E. And I have another vector here. Let's call this vector B. So the resultant vector, which is R, is equal to A plus B. The parallelogram law is stating that if two vectors A and B are added together, then their resultant is the diagonal of the parallelogram. So assume I join these two vectors A and B to look like this. Vector A, vector B. Mind you, these vectors have a direction. If I should draw an imaginary line here, we realize that it describes an angle here. And when I also draw an imaginary line here, we realize this vector also describes an angle here. All right, now we have managed to put these two vectors together. Then what is the property of the parallelogram? We know that parallelogram, they have two opposite parallel sides. Their opposite sides are always parallel. So what I am going to do is that I'm going to complete this parallelogram. Okay, so I am completing this. So this means that there has to be another arrow, or another side of the parallelogram should be parallel to this side, and the other end of the parallelogram should be also parallel to this side. That is what I mean by the two opposite sides should be parallel. Okay, now should I complete this one? I will get this. Not very perfect, but we can manage it. And then another parallel line to this line here. Let's see. Okay, let's do it again. Okay, so this is how it's going to be like. After I complete the parallelogram, it's going to look like this. All right, so we've been able to complete the parallelogram, and the law is saying that after that, the diagonal of that parallelogram is the resultant of the two vectors. So suppose that I draw a diagonal here, I'm going to get that diagonal to be the resultant of the parallelogram. In other words, if I put the diagonal here, it's still going to give me the same value, right? Okay, so let's say I draw the diagonal of that parallelogram here. Okay, let me draw it here. Let me put it here. You can either draw it here or here. They are still diagonal. All right, so the diagonal, so let's say this vector here was the vector E, the vector here was the vector B, and now we have this diagonal part, which is a vector R. The diagonal part here to be vector R. So we can say confidently that this vector R here is the resultant of the two vectors A and vector B. I hope you understand it. All right. So back to this example here. We have vector A here, we have vector B. Then this is the resultant. How did this R become the resultant? So first, we have to complete the parallelogram. By completing the parallelogram, we know that there should be two opposite parallel sides of each of them. So we complete this one here. We complete this side of the parallelogram, right? And then the opposite side of this, the B vector, is here. So when the parallelogram is completed, the diagonal here, which is the R, becomes the resultant. That is why you only see it that way. Then in other one, we have this is for the addition of the vectors. Suppose that A and B, they both have positive magnitudes, and then in this case we have A minus B, A and then minus B. Because it is subtraction of vectors, let's assume that we are subtracting B from A, assuming the magnitude of A is greater than the magnitude of B. All right, in this example too, we have the arrowhead here, then one arrowhead to here, right? And then the resultant is described here as the R. So how did we come up with the resultant? We know that for the parallelogram law, we are supposed to complete this parallelogram and then find the resultant. So in completing the parallelogram, we have this line here, and then one parallel to the B side. Then when those two lines are completed, then we can see that the diagonal, which is described by the R, becomes the resultant of the two vectors. Okay, so mostly after finding the resultant here, when the parallelogram is drawn to scale, then it means that the resultant here, which is R, will give you the exact value that you want to find. And in another way, if the arrows here are not drawn to scale, as in the ones here, since they are not drawn to scale, before we can actually find the actual resultant, then we will have to use either the sine rule or the cosine rule, and it will help us to find the magnitude of the resultant. But finding the magnitude of the resultant using the sine rule or the cosine rule will be a lesson for a different day. But for now, our focus is on how to know or how to determine the resultant of addition of of the addition of vectors and the subtraction of vectors. So when it comes to parallel vector addition, the addition of parallel vectors are straightforward. When we say parallel vectors in this sense, then it means, assume I have a vector, assume that I have a vector A going this direction, vector A, and then another vector here, let's say vector B, in the same direction. Then I can say that the resultant, which is R, is by simple arithmetic, which means that the resultant is going to be vector A plus vector B, vector A plus vector B, since they are all moving in the same direction, which is to say that, assuming that vector A is 4 units, assume vector A is equal to 4 units, vector B is equal to 8 units, or let's say vector B is also equal to 4 units. Then the resultant here is going to be by simple arithmetic, which is the resultant here is equal to 4 plus 4, which will give us 8 units. In other words too, if vector A, let me use the plain sheet. In other words too, if vector A is moving in one direction, and then let's say vector B is moving in the opposite direction, then assuming that vector A is equal to 4 units, and then vector B is equal to 2 units, then we can say the resultant of these two vectors, which is R, is going to be vector A minus vector B, because assuming that moving from the left to the right is positive, and moving from the right to the left, from the right to the left is negative, then A has a higher magnitude than B, then the resultant is going to be A minus B, which will give us 4 minus 2 and is equal to 2 units as the resultant. This is only possible, or this is only for vector quantities that have the same direction and are parallel. However, in the case of vector addition, such as the one described earlier, that is moving at different angles, assuming one for this and then another one here, moving in different angles, we know they are not parallel. One, they are not parallel. Two, they are all having these different angles, right? So in cases like this, for you to find the resultant, then we should consider completing this using the parallelogram law, which will be like this. You complete the parallelogram, then we draw the resultant from one side to the other side. So this resultant here is what is going to be the resultant for these two vectors here. All right. However, if it is parallel, if they are all moving in the same direction, then it's going to be by simple addition. But if sorry, but if they are moving at different angles, then we complete the parallelogram, and then we determine where the resultant is going to be. After that, for you to actually find the magnitude of the resultant, is either we use the sine rule or the cosine rule. In some instances too, we can use the Pythagoras theorem to find the solutions or resolution of forces. There are lots of ways that we can come up with how to find the resultant, and we will look at them in the next session of this lecture. Okay, so the difference between the straightforward parallel vectors and then the ones that have angle is that for the parallel forces, we just add them by simple arithmetic. But with the ones that have angles, that have different angles, we have to consider using the sine rule or the cosine rule. So what is a resultant vector then? We have been talking about a resultant vector. Then we say that what is a resultant vector here? And I'm saying they say we have two components of vectors A and B acting at a point can be added together to form a resultant vector. That is, the resultant vector is equal to the vector A plus the vector B. Okay, that's for two vectors. But if we have three vectors, then it says that if three vectors A, B, and C act at a point, say O, then the resultant R of any two of the vectors is found. Say R is equal to A plus B, then R is equal to A plus B. Then we say that the resultant is then added to the third vector C to give the total resultant RT of all three forces. So to explain what was said earlier, this is what it means. It says that if we have three vectors, let's say I have three vectors. The first one is E, then the next one is B, and then the last one is vector C. So how do I find the resultant of all these three vectors? So we put them together. We have vector A here. We have vector B going this way, and then vector C coming this way, and assuming they are all acting at a point O here, then how do I find the resultant? So before you find the resultant, one, you must find the resultant of any two of these forces. So this is more like a graphical approach. Find the resultant of any of the two forces. After that, you add that resultant to the third vector. So you find the vector of any of the two vectors. That's the resultant of any of the two vectors. Then that resultant is added to the third vector to find the total resultant. That is to say, assuming I have these vectors here, A and B, then to find the resultant of these two vectors, as it has already been said, we describe the parallelogram for this. We complete the parallelogram here, then here. Then with this, I know my resultant is going to lie somewhere here. Right? Good. So this is the arrow here, which is R, is the resultant of vector A and vector B. So I can say R is equal to A plus B to give me this vector here. Now, I also want to find the, now I've dealt with A and B, but C is left out. Now we have to include C into the resolution or finding the resultant vector. Now what we are going to do is to consider the next two vectors, which is R and then C, because A and B, this is their resultant. Then the resultant of R added to the vector C here should give us the total resultant that we will seek to have. Okay, so complete let me complete that one too. Let me complete this parallelogram as well. That is between R and C to look like this. Okay, and now we can have our resultant. And now we can have our resultant here. So let's say this one now becomes our total resultant, say RT. So this will now become the total resultant of adding vector A, vector B, vector C by per the parallelogram law. So first we have the three vectors here, A, B, and C. Then two, we find the resultant of any two of the vectors. Let's say vector A and vector B. We find the resultant of them using the parallelogram law as R here. Then after finding that, we use the resultant that we found from A and B, then we add it to vector C to find the total resultant, which is giving us vector RT to mean the total resistance. So in summary, we say that the first resistance is equal to, sorry, not resistance, resultant. The resultant vector was R equal to A plus B, and then the total resistance here, RT, is equal to R plus C. All right, so the total vector addition A plus B plus C is going to be R t, which is equal to r plus c, this one. Okay, so this is how you are going to, so assuming that there are multiple vectors, this approach is going to be used, and it goes on and on and on and on. So if we are having 4 vectors acting, let's see, one here, another one here, another one here, and another one here. See, E, B, C, D. Then using the parallelogram force, the parallelogram law, we are going to complete this one first. We complete this one, then we know that the resultant passes through here. That is for A and B. Now we add this resultant to C, so we complete the resultant for the parallelogram for R and C. Let me call this one R1, resultant 1. Then we complete the parallelogram with C and R1 here. So we are going to get another resultant here, which we might call R2. Then with R2, we have to complete that parallelogram with D. So it's going to look also like this. Sorry, let me make it a bit more accurate. So let me change the color. So for this one, it has to be parallel line to R2, which is here, and then parallel line to D, which is also here. So it means that when we do, after finding the parallel line, drawing the parallel line, say, then the resultant is going to lie here, that the diagonal of the parallelogram, that gives us R3. So that is that. So if there was to be another vector, then we complete the parallelogram, and it continues in that order till. So this is the introduction to the vectors. Now we've talked about quantity. We said that quantity is anything that can be measured. We looked at the scalar quantity, which is made up of just one quantity. We looked at the vector quantity, which is the scalar quantity it has only magnitude. Sorry, we looked at the vector quantity, which has both magnitude and the direction. Then we also talked about fundamental quantity, which is the basic form of quantities that can be measured. The derived quantities, which is a combination of 2 or more fundamental quantities. Then we also looked at vectors, and then we said vectors, they have both magnitude and then direction. We looked at how to represent vectors by the arrow, and then described by an angle to show its direction as well. And then we've come to look at the addition and then the subtraction of vectors, and we've seen that addition of vectors, before you do that, you have to complete the parallelogram per the parallelogram law of addition. And then when we're able to do that, we can find it using the sine rule or the cosine rule, which will be discussed in the next video. And then for parallel forces or for parallel vectors, their vector addition is quite simple and straightforward. It's just by simple arithmetic, then that is that. And then we've also looked at resultants, and we are saying that we are just talking about resultant, how to resolve or how to find the resultant of multiple vectors. And we've described how to find the resultant for 2 vectors, how to find the resultant of 3 vectors, and now how to even find the resultant of 4 vectors, and so on, using the parallelogram law. And if you want to use the parallelogram law to find the magnitude of the resultant, then should you do it by measurement, or let's say should you do it to scale, then the resultant described by the diagonal of the parallelogram is the magnitude, that is the length of that arrow of the resultant, which is the diagonal of the parallelogram, to give you the magnitude for the resultant. So guys, thank you very much for watching the video to this point. If you enjoyed it, I hope that you will click to subscribe, you like the video, share to your friends so that they can also benefit from this video.